The desert sun, focused beyond the boiling point to make electricity. In this solar power plant, it's all done with mirrors. 3/4 of the known universe is hydrogen, but just a little in a fuel cell takes this ride a long way. Ever feel like you're just a small cog in a big machine? Well, hop on the escalator and join the crowd. 3,000 needle stabs a minute. If you're not cringing yet, wait till you meet the tattoo gun. Let's take the lid off these machines and see how they work. There are a lot of ways to harness the sun's power, like with a magnifying glass or a curved mirror, both of which can concentrate sunlight into intense heat. And that's exactly what inspired the creators of the Solar One to build a low-emission power plant out here in Nevada's Mojave Desert. Let's see how it works. In a desert where the sun shines 300 days a year, 200,000 mirrors side by side, row on row, form hundreds of parabolic troughs, reflecting sunlight with a surface area of about 50 football fields. That makes enough electricity to keep the power on in 14,000 homes year-round. So yeah, we're talking solar here. But not the pricey silicon cells that run our calculators. At this scale, that would cost a fortune. This is sunlight concentrated 70 times its normal strength, hot enough to burn your skin instantly. But here, it's focused on heating oil inside these tubes. And that hot oil is harnessed to boil water, which makes steam that drives a turbine, which makes electricity. Simple, right? Well, before you go out and build one, there are a few problems to overcome on a solar power plant like this. Number one, regular mirrors at home don't reflect nearly enough light to do the job. Two, your mirror has to move all day. The sun, that is the Earth, won't sit still. And finally, what do you do with a solar plant at night? Okay, first challenge, the mirrors. Household mirrors are fine for touch-ups, but are backed with a cheap spray-on coating that absorbs a lot of light. Pricey laboratory mirrors use silver coatings that reflect most of the light that hits them. And the ones here take it up another notch, reflecting almost 100% of the light that strikes them. To heat things up even more, they're curved. This concentrates the light onto the oil tubes that sit perfectly at their focal point. Focusing light is one thing. Putting it to work, another. So engineers clad the oil tubes in a special glass that intensifies the sun's rays even more. By the time the hot oil travels through nearly 20 kilometers of tubing, it's 4 times hotter than the boiling point of water. That's twice as hot as the oil used to make fries. The oil's now pumped into the guts of the plant and is ready to boil water. Oil tubes run down the center of these water pipes. The water absorbs heat from the oil, turns to steam, and heads straight to the machine's generating station. All of the electricity from this power plant is produced with conventional steam turbines. Steam drives the blades, which spin a generator, which delivers electricity to the local grid. Once the steam has fueled the turbine blades, It cools down and loses its, well, steam. It's not hot enough to drive anything, but it's still vapor. It's got to cool down before it can be used again. So it heads to a rain room, where steam is trapped, condensed, and returned to the system. The second challenge for this machine is to follow the sun's arc. Sunflowers have to move all day in order to capture the sun's energy. If these mirrors were stuck in one place like a traditional solar panel, they would only reach their maximum potential for a few minutes a day. So, electric motors are placed within groups of mirrors that allow them to follow the sun's arc. On to the third challenge. What happens after sundown? No sun, no power. There are plans for thermal storage tanks filled with heat-trapping molten salts, but they're still on the drawing board. So at night, the Solar One switches to this natural gas burner to keep the turbine spinning. Good thing that demand for electricity peaks during the day. And that's when this machine delivers. And boy, does it deliver! 60 megawatts of power with almost no emissions, preventing 20,000 cars worth of CO2 from entering the atmosphere every year. The Solar One, a giant machine with a small footprint, capturing energy from the sun. It's no magic trick, but it is done with mirrors and no smoke. This motorcycle is powered by hydrogen, the simplest and most plentiful element in the known universe. Its creators called this bike ENVI, short for Emissions Neutral Vehicle, and you can make a cup of tea from the only thing that comes out of its exhaust. You guessed it, water. And what makes the ENVI go? Is this mini power plant called a fuel cell, which produces enough electricity to keep the bike rolling. Not bad for a machine that can hit 80 kilometers an hour. Okay, so it's not exactly a rocket, but it is fueled by rocket science. The first practical fuel cell system was developed by NASA in the early 60s to generate electricity in space capsules. A good way to understand fuel cells is to see how hydrogen is produced, and it's actually pretty simple. Fill a container with water and run an electric current through it. This splits hydrogen and oxygen from the water molecule, and the process is called electrolysis. This is the science behind producing hydrogen gas. Now, if you reverse that process and figure out how to rejoin hydrogen and oxygen, you'll create electrical energy along with water and a little heat. But it's not a fuel cell yet. You need to figure out how to harness its electrical energy. And to power this bike, it needs to be compact and portable. Here's how it works. These vents near the handlebars stream outside air to the fuel cell. The attraction between oxygen and hydrogen helps the fuel cell produce electricity. And that's all about electrons. Electricity is simply a flow of electrons. A fuel cell's primary function is to liberate them. Hydrogen enters the fuel cell on the left, oxygen on the right. A platinum film strips electrons, in yellow, from the hydrogen leaving behind protons. Both are attracted to the oxygen on the other side, but electrons are stopped by this membrane. They now need to find their way back to the protons. The only way out is along wires to an electric motor that spins a drive belt and gear on the back wheel. After passing through the motor, the electrons find their way to the other side of the fuel cell. As they meet up with protons and oxygen, they form H2O, a chemical soup known as water. That's the only emission this fuel cell belches out. And save the jokes about this having a sewing machine engine, because this puppy could power 60 of them. Okay, the ENV is powered up. How do you keep it going? Simple. A fuel cell will go on forever, so long as it has a source of hydrogen. When the fuel cell runs out, all it needs is a fill-up, and there's a ready supply of it here, at Loughborough University in England, where this prototype was born. Filling up a fuel cell is as exciting as topping up the gas tank in your car, minus the fumes. And unlike a conventional motorcycle, the only sound you'll hear from this machine is the rubber on the road. We're still a few years away from hydrogen-powered vehicles in the local parking lot. But when we get there, you may have your own personal fuel cell to power or charge just about anything, anywhere. And oh yeah, a motorbike too. This is the Great Cattle Drive. Day in, day out, over and over again. In some office somewhere, flow dynamics experts study our patterns to get us onto a machine that's basically a tricked-out set of stairs on a conveyor belt. So, how does it work? Escalators not only get us upstairs, they process crowds without damaging the goods. Today's escalator designers have 3 major challenges: keep it running smooth, quiet, and safe. Powering a busy escalator is like pulling a fully loaded SUV up a 30-degree hill. But under this machine, there's nothing but a puny 10-horsepower motor. How is that possible? Sure, it spins fast, but there's no way it can drive a fully loaded escalator. It was installed because it's whisper quiet. And that's important if you want people to use them in public spaces. Going with a larger direct drive motor would make way too much noise. So to generate enough power, this little guy needs a gearbox. The gearbox steps down the motor's RPM, and that translates into increased horsepower to the larger drive gear. And when you tow anything up a hill, power is always better than speed. But this is also a powerful, potentially deadly machine, and fatal accidents still occur around the world on a regular basis. Tumble into one of these, and you may as well fall into the jaws of a shark. And that's no joke. Escalator accidents kill more people per year than sharks. So when it comes to safety, designers look at every inch of the escalator, especially at the 2 trickiest parts of the ride: how you step on and off the machine. To make life easier, they came up with the level loading platform. This design feature remains flat for the first few steps as you walk on, and gives you a moment to adjust before the step beneath you rises. Some early escalator models force patrons to jump onto the first rising step. Not exactly the challenge you're looking for at a shopping mall. Each step has upper and lower wheels on its ends, which fit into 2 sets of tracks. The upper set of wheels join together to form parallel chains in a continuous loop. This chain of wheels fits into a cog of the main drive gear and into notches in the main drive wheel. The steps rise and stay level through the ride at 1 to 3 kilometers per hour, then collapse to let you off. While riding, you hang on to flexible handrails. They have their own rollers and their own path, but are driven by the same drive mechanism as the steps, so they stay perfectly in sync. Other welcome design features on this machine are the comb plate and the step grooves at the end of the run. They work together to keep loose shoelaces, debris, and curious little fingers from getting caught. And if the handrail ever goes out of sync, if anything gets jammed or slows it down, or if the impact sensors in the comb plate sense anything wrong, the brakes will bring everything to a safe stop. The Escalator first appeared as an amusement park ride in 1896. Today, they give over 90 billion rides a year in North America alone. And the only time we ever notice them is when they break down and we haul ourselves and our assets all the way to the next floor. Tattoos have been around for thousands of years, and they've never been more popular. One in 8 American adults have at least one tattoo. That's 40 million people. Which is pretty crazy when you realize how much it hurts to get one. And well, they're kind of permanent. It's a mechanical rattlesnake that spits ink instead of venom. So how does this machine work? On the surface, tattoo machines are pretty basic. You can build one using a motor from a hairdryer or a vibrating toothbrush with guitar strings and erasers. And your ink can be taken from a simple ballpoint pen. Or you can sharpen a stick, put dye on the end, and poke holes in your skin. Just don't go trying any of this at home. All you have to do to make a tattoo is puncture the epidermis, or outer layer of skin, and deposit color into the dermis, or second layer of skin, about 1 millimeter below the surface. And this machine does it up to 50 times a second. Which means for every minute in the chair, you're getting stabbed 3,000 times. And if it takes up to 3 hours to create one, that's 540,000 punctures. Ouch. Then there's the problem of accuracy. You can't make detailed art like this without micro-precision. The tattoo machine controls needle depth, speed, and application to within a fraction of a millimeter. It hurts like a dental drill, sounds like a dental drill, and is as precise as a dental drill. It starts with a bunch of parts and one elastic, divided into 3 main sections: the base, the mechanism, and the needle. The business end is, of course, the needle. It's soldered to a metal arm that connects to the armature bar, the part that does all the work going up and down. A spring connects the armature bar to the base, the hunk of metal that looks like a rabbit ear with a screw in it. And the elastic? It keeps the hyper-fast needle from going off track. No coloring outside the lines here. The tattoo machine is armed with razor-sharp stainless steel, not tipped with a simple sewing machine needle. Modern tattoo needles come in a wide array of designs. They may look medieval, but are created to deal with some amazingly intricate and, well, special requests. The needles make tiny successive holes in the skin. Picture a sewing machine working through fabric. The ink is deposited into skin just like the thread that creates a stitch. The skin has to be stretched tight during the process. If left loose, the needles get stuck, the ink bleeds out, and makes a mess. Let's see how it works on a new design. It begins with an outline. In order to trace it, the machine is set up to draw a fine line. So, it's loaded with a needle that's round like the tip of a pencil. After the outline is complete, it's time for shading. So the machine needs a new set of teeth. Shading needles are configured like a comb. The more needles in a configuration, the more ink is transferred. The multiple needles create matching holes that are filled at the same time. The needles get up to speed by harnessing electromagnetism. And that's controlled by this power supply. A foot pedal turns the juice on and off. This drives the machine at rates of over 4,000 revolutions per minute. A sports car can hit 150 kilometers an hour at the same RPM. Power travels along cables to these coils and creates a magnetic field. This pulls down the armature bar and forces the needle into the skin. As soon as the armature bar hits the coils, it breaks the electrical circuit. The magnet turns off, and this spring snaps the bar back up. As soon as it hits this contact, the magnet is reactivated and the needle is driven down again. The rate of the needle in this machine is so fast, it matches the wing speed of a hummingbird. But birds' wings do not cause sharp, burning pain. In a world where everything is disposable, these works of art are for keeps. Whether for social prestige, spiritual devotion, tribal rite of passage, or a momentary lapse of reason, tattoos are the ultimate visual sacrifice for personal expression. This machine has taken an ancient art form and made it perfect with a little modern know-how. A massive city on a deadly floodplain. London's Thames barrier holds the line against powerful storm tides. It's the most powerful and durable locomotive working today. The diesel-electric is a workhorse and power plant all in one. Ever wonder what's going on under your feet when you're pumping gas? Inside the self-serve gas pump. Win, place, or show. When it's nose-to-nose and stakes are high, all bets are on the photo finish camera. Let's take the lid off these machines and see how they work. This is the Thames water barrier, the single most important flood defense system in the world. There are other barriers, but none come close to this machine's burden of protecting over 1 million people and billions in real estate. Its job is simple: stop a river from putting London underwater. Let's see how it works. Stretch a set of gates 520 meters across the River Thames to block it. Now, do it in just minutes as thousands of tons of water rush towards you. Then, when the threat's over, retract the gates quickly to let boat traffic through. And keep it working for decades without ever breaking down. The barrier was first used in 1983 to halt a storm surge from the North Sea. Surges that slam into the mouth of the Thames are a huge threat to London. Combine a storm with the river's high tides, and you've got a major disaster. Big parts of London would be swamped by floodwaters. So, to protect people and the city, engineers had to figure out how to block the Thames while maintaining its shipping channels. Their first big challenge was location. They chose a spot 15 kilometers from the Houses of Parliament, where the banks are straight and the riverbed sturdy enough for a massive concrete foundation. There are 10 gates in total that span the Thames. 6 sector gates that rise from the river. These include 4 large central gates and 2 outer ones. There are 4 smaller gates by the riverbanks that live above the water unless they're in use. All of the gates are hollow and made of steel. They fill with water when submerged and empty when rising from the river. Each of the 4 large gates is a hefty 3,300 tons, almost half the weight of the Eiffel Tower. The next challenge was how to get the gates out of the way quickly and safely. These radial arms drive the sector gates under the water to lie flat in concrete sills on the riverbed. This allows the free passage of river traffic. If forecasters spot a threatening storm, they notify the Port of London so that shipping in the area can be given the heads up. Red X's on the barrier tell ships to stay put. Operators in this tower control the movement of the gates. The closing sequence is designed to work with the natural flow of the river. After the outer gates are dropped, the sector gates are raised in pairs from the outside in. If the command center's computers were to crash mid-emergency, each pier has its own set of independent controls. And if they fail, the rams can be manually cranked. With millions of people and billions in property behind this barrier, nothing's left to chance. Even these radial arms are doubled up. Each one is powerful enough to move a gate on its own if the other arm breaks. They're powered by sets of hydraulic pistons. The top arm pulls in, while the bottom one pushes out. This rotates the sector gates up and into a defensive position. Operators normally close the barrier in about 90 minutes. In an extreme emergency, the entire thing can be set in place in just 15. But if you shut it all at once, the force of the entire river hits the barrier at the same time. And that could send a deadly rebound wave back downriver. If floodwaters ever threaten to top the gates, they're raised a little more to allow a controlled amount of water through. This is called an underspill position. It kind of acts like a dam controlling the levels of a reservoir. The closest any flood has come to topping the barrier is 2 meters. So far, so good. The entire operation is electric and has 3 independent sources of power. Electricity from the grid flows through cables in tunnels beneath the river. If the tunnels flood or power gets cut, there are 3 backup generators, each powerful enough to operate the entire barrier. The electrical bill for 1 turn of these screws? Almost 6,000 euros. On to the final challenge. The gates need constant maintenance to fight rust and water damage. How do you get that done without shutting down? By designing the whole thing for high and dry repairs. The gates come with an extra hydraulic piston to rotate them up and out of the water, so workers can repair damage and touch up the paint job. The gates do spend most of their time underwater, so paint is needed to fight rust. It takes about 40 tons of paint, figure 10,000 cans, just to cover one of the 4 large gates. The barrier has averaged about 5 closures per year since it opened. But if forecasters are right, there could be as many as 30 per year in the coming decades. And that's quite simply because water levels have been rising steadily. Only time will tell how long this astounding work of engineering will hold up. It's among the most powerful, most durable train engines working today. The diesel-electric locomotive is a workhorse and power plant all in one. It can haul thousands of tons of cars at speeds of up to 200 kilometers an hour. And it can work on almost any type of track because it produces its own power. The word locomotive means self-propelled vehicle. And its challenges have always been the same. Create enough power to move cargo and people, haul them quickly and efficiently over distance, then stop them smoothly and safely. Let's see how it works. Straight electric locomotives need power from the grid to move. To keep them in business, you need expensive and hard-to-maintain overhead wires or electrified rails. But not all rail lines are connected to the grid. And if you're rolling on them, you need a diesel-electric locomotive, like this one. Producing power is straightforward on this machine. A diesel engine spins a generator that produces electricity. The electricity flows to traction motors on each of the axles. And they spin the wheels. You'd think it would be easier to get the engine to directly spin the wheels, like in a car. But then you'd need a massive transmission to handle different torques, speeds, and loads. The transmission would have so many gears, you'd need another train car just to carry them. Electric motors don't need transmissions. Increase the flow of electricity, and you increase their speed and power. Simple as that. A 16-valve diesel engine that puts out about 3,000 horsepower, spins a generator that produces over 2 megawatts of electricity, enough to keep 500 homes lit up year-round. That's a lot of juice, and it all goes to the traction motors located on each axle. This locomotive weighs in at 80 tons and has enough power to move over 30 times that amount. That's a lot of weight riding on the rails. So these machines rely on steel wheels to stay online. Other materials, like rubber, would warp and burn a lot of the locomotive's energy just to overcome friction. But this material has some problems of its own. Steel on steel is very slippery. And when shaped like this, all that weight can balance on the surface area of a dime. This helps with efficiency, but it sure causes problems with traction. Going around corners isn't an issue because the wheels have flanges to keep them on the track. But what about accelerating? To get started, engineers blow sand onto the tracks to give the machine all the grip it needs. The real work for this machine is managing all that weight when it's moving. To stop an object in motion, you have to convert all its kinetic energy into something else, like heat. A speeding bullet has way too much energy for glass to stop it. But thick steel is able to convert the bullet's energy into enough heat to melt it. Try stopping a locomotive pulling a full load of cars traveling at 200 kilometers an hour. Its kinetic energy is equivalent to 1,000 kilograms of TNT. Which is why fully loaded trains need about 2 kilometers to stop. When it's time to slow down, power to the motors is cut off. The wheels are now spinning the electric motors. This bleeds energy from the wheels, and they slow down. It's called dynamic braking. Most of the kinetic energy from the wheels is converted into heat that's dissipated through onboard resistors. Air-powered disc brakes also help out. Their spring-loaded pads are held open by air pressure. When you activate the brakes, the air pressure escapes and the pads close on the disc. And there's always sand available if they need more traction. What happens if the engineer falls asleep? This thing's basically a bomb on wheels. Which is why most locomotives come with a dead man switch. Unless the guy driving this thing hits this button every 30 seconds, an alarm sounds. And the machine automatically shuts down. The locomotive has been a giant in the transportation business for almost 2 centuries. Pound for pound, it's still the most efficient way to move goods and people over land. And thanks to the latest innovations, it shows no signs of giving up its crown. Gas stations pump out billions of liters of gas every day around the world. At one time, gas station employees had to do the pumping for us. And it's thanks to this vending machine that we now get to do it by ourselves. The self-serve fuel dispenser is like a robotic bartender. It measures, mixes, pours, calculates, and then gives us the bill. And because we're the ones handling a hazardous cocktail, this machine also makes sure we do it safely. Here's how it works. When we squeeze the handle and pour, 3 questions. How is the accounting done? What makes it stop when our tank is full? And if there's a spark, what prevents the tank and us from going up in flames? Gas pumps can deliver the goods in multiple grades, but they usually offer 3: regular, mid-grade, and high octane. The fuel comes from subterranean tanks that can hold up to 50,000 liters each. Most stations have 2. One stores regular, the other high octane. So where do the other grades come from? Simple. The system just mixes fuel from the 2 tanks and delivers exactly what you order. No matter what button you push, this little device gets it to your car. A submersible pump draws in the liquid gas and sends it out through a hose that connects to the nozzle. As soon as that happens, the counting begins. Along its path, the fuel fills a flow meter, a metal chamber that contains a rotor. It's called a pulsar, and it measures 1 liter of gas every 4 turns. An onboard calculator multiplies that number by the gas price and displays your running total. But there are problems with measuring gasoline and getting your money's worth when the temperature outside rises or falls. The density of gas shifts 1% for every 10 degrees of outside temperature change. If it heats up, gas expands. Cools down, it contracts. So if the temperature goes up during the day, you're going to get less gas on the drive home. Fortunately, these probes keep track of changes in temperature and regulate the flow of gas according to where the mercury is at. Meanwhile, we're squeezing the nozzle for all it's worth to get this over with. How does the pump know when to shut itself off? The gas pump comes with an auto cutoff system. It's a small tube that runs from the outside tip of the nozzle up to a sensor inside the handle. As your tank fills up, the nozzle becomes submerged. This chokes off the air pressure that was holding the handle open and shuts down the flow of gas with a familiar click. This is what protects us from getting splashed with liquid fuel. But how does it protect us from the explosive gasoline vapors that are released during pumping? A small motor is used to create a vacuum that sucks excess vapor from the nozzle. But the machine can't capture all the vapor, and that means there's always potential for danger. When sliding in and out of your car, you can create static electricity. If that hits the vapor, watch out. It's no urban myth. It happens. Luckily, gas vapor needs oxygen to burn. That means the flames could never reach the oxygen-free fuel tanks. Not enough O2? No explosion. Same goes for inside your tank. And when you get back in the car and turn the keys, you'll see this. That's because a styrofoam float has made it to the top of the tank, pushing up a metal rod that sends an electric signal to the fuel gauge, signaling that it's full. So the next time you're filling up, relax. There's a lot going on under your feet and in the box beside you to make sure the only bad thing about the experience is how much it costs. This is a digital photo finish camera, found at the end of every major race. It's a machine that can help make you a fortune or break your heart and bank account. Whether it's pointed at men, machines, or animals, there's no arguing with its results. Even if these photos look nothing like an average snapshot. Let's see how it works. Photo finish cameras do 3 things that normal cameras can't. Fit the end of an entire race into one frame, capture the exact moment each one crosses the line, and get a clear shot of all the competitors, even if one blocks another from view. But the photo finish camera doesn't just hang around waiting for the finish. An internal stopwatch is triggered inside the camera at the beginning of every race. And measuring them isn't just about the finish line. For results to count, competitors have to start on an even foot. At a horse race, the photo finish camera needs a starting gate. After the horses are loaded in, spring-loaded gates are shut and locked in place by these arms that are connected to a magnetic roll bar. When the starter hits the button, the magnet turns off, the bars release, and the gates fire open. And this machine stands by, ready to fire. It's an ultra-precise, ultra-sharp camera that costs about 8,000 euros. But you wouldn't want to use it for your vacation pics. It takes images that are just a few pixels wide, the perfect width to capture the finish. Just before the horses hit the line, the operator presses a button and the camera starts firing at up to 3,000 frames per second. Each line image gets fed to a central computer, which arranges them side by side. Add it all up, you get this, the ultimate collage. That contains as many as 50,000 photographs. So while a normal snapshot shows one moment in time, a photo finish actually shows one location spread over many moments in time. Its high perch gives the camera an excellent angle on the proceedings. But there's always a chance of this: two bodies floating in the same digital space and time. So the camera uses a trackside mirror to produce a reverse angle. This captures all the horses, no matter where they are. Nothing escapes its digital eye. Once the last horse crosses the line, the operator edits out gaps so all the competitors fit on one screen. This image may be all gamblers and fans care about, but this machine knows a world record could also be on the line. As the photos come in, each one is tagged with a time, more accurate than 1,000th of a second. Line up the cursor with any competitor, and it tells you the exact moment they cross the line. This is what announcers mean when they say they're waiting for an official time. Totally unbiased, never blinks an eye, and it always tells the truth, one line at a time.